see whether I can share the stuff from last week to show you where we were at. Let's see. Oh, I still haven't. Oh my God, yeah. Like, let me join the. Forgot to join on Zoom here. Yeah, like, yeah. Yeah, oh my God, let's see. Now I have to approve it. Like, can't just do it. These things can take forever. No, okay. I approve it. No, other people use the device. And then meeting info. Yeah, I know. I'll probably finish a bit early today anyways, but think of that. Okay. Okay, now we're good. Now this looks good. Okay, yeah, so first what I was going to show you was the example I was trying to work on in the last few minutes of the previous class, and then I'll show you like an two dimension, which is like more like of the general case. Before we continue talking about like more of like these equivalence relations, I'll give you some more examples today, like in linear about equivalence relations like for linear algebra and topology. I also post kind of like some problem for you to look at later in the week. I was just trying to like play with something else like earlier on. But let's see. Okay, where is the definition? All right. So what I was saying is that right, like an equivalence relation, just to remind you what it was, that it's a relation that we establish between different objects, right? So, and it has to satisfy three properties. So the first one is like this symmetry, which is that if two, like, if two objects are related, it doesn't really matter in which order the relationship goes. So I think the example I had given was like with the friendship, right? Like where if Alice is friends with Bob, then assuming like normal concepts of friendship, then Bob is friends with Alice, right? But parenthood is not symmetric, right? Because if Alice is Bob's mother, then Bob is not Alice's their father or whatever. So like a symmetric relation, it doesn't matter. It kind of goes both ways. And then the other two important properties in order to be an equivalence relation was that it is transitive, right? Meaning that, if X is related with Y and Y is related with Z, then X is related with Z. So like the example, like with the friendship that wasn't transitive, right? Because usually friendships are not transitive. If Alex and Bob are friends and Bob and Charles are friends, it's not necessarily the case that Alice and Charles are friends. They may not even know each other. So friendship is something that's typically not transitive. But the example that I was like mentioning like last time about like a student's major, that would be a transitive relation, right? Because if two students are related, if they have the same major, right? And if Alice and Bob have the same major and Bob and Charles have the same major, that basically forces Alice and Charles to have the same major, right? And the other property required for an equivalent relation is like this reflexivity, which just means that every element is related with itself. So again, in the major example, it just means like you have the same major as yourself, which sounds kind of like silly if you say in those terms. but there are other relations which are not like reflective, like, I think I mentioned like the one about being a tutor. You typically wouldn't say that you're your own tutor, like usually that's reserved when there's a distinct person who is your tutor. Okay, so they are very useful, these equivalence relations. You see why, because later on in this week, in fact, because it can be used to construct other um they show up in different places, but kind of like the example I was giving you a little bit more like kind of like from like a data science point of view, like a very baby example is related to this clustering thing, which we'll go into more depth later on when we talk about persistent homology. But the idea, again, just to put very concrete things, like very concrete numbers, like you could imagine you have like 9 data points, and this is how the 9 data points, you know, are aligned on the number line, right? So one way you could try to, you could create an equivalence relation is to say, well, you would say that 2 points are related if the distance between them is below a certain value. Okay, so if the distance, or rather like if the distance is at most a certain value. So for example, if r equals 1, that's the one I was mentioning, that in this case translates to saying that 2 points are related if their distance is less or equal to 1. That is almost an equivalence relation. The problem is that it fails in the transitivity, right? Because -4 and -3 are related because their distance is at most 1, and -3 and -2 are related because their distance is at most 1, but -4 and -2 are not related because they're now 2 units apart. So the fix to the equivalence relation that I was mentioning is that you just say, okay, to make it a transitive, you just allow for chains to take place, meaning that, not you say that they're related, 2 points or 2 members are related, if you can connect them with a sequence of points and between any 2 elements, like a path, all with distance that's or equal to 1. So that's actually going to be that's actually a way to fix a relation that's symmetric and reflexive in general. If it's not transitive, you can kind of like make it transitive by just like allowing kind of like these paths to take place. So for example, if you do it, I think I think I had it here. If you do it with r equals 1, now all these points are within distance 1, or can be connected on points like that differ by distance 1 from one another, right? So you would call that kind of like a cluster. And the same happens here, right? Like they're either at distance 1, when the one in the middle, they're either at distance 1 or connected by paths of distance at most 1. And same happens with the last cluster, right? But like, for example, the reason why the purple and the green were not related, right, is because from going from -2 to 1, I do have to make a jump that is a step of size 3, and there are no intermediate points that kind of help me connect, kind of like a bridge, like that goes from -2 to 1. And kind of like the perspective, kind of like a lot of the philosophy of this course is that you kind of like give yourself a value. In this case, a value, you can think of it as being this distance of 1. But there's nothing special about the number 1. So you can like study what happens as you vary the value, which is what I'm doing here. So instead of you have chosen the value 1, you choose the value 2, right? Then this still kind of like its own island or cluster, but now the last 2 blocks can be connected, right? Because I can jump from 3 to 5 using a jump of size 2. So all of these kind of like get merged into the same cluster. And then if you can increase it by another value, right? Then say with value 3 of distance 3, then that's already enough to connect all of them together, right? So the idea is that kind of like in this problem, what you would have done is kind of to study as you vary the value for r. I kind of like did these great jumps here, but of course you could have done it continuously, right? As you study the value for r, you just kind of like see how they kind of like get separated into regions, like if you want to think of this as kind of regions in space. It's like kind of like it says, there's like, of course, like a more complicated example. I just started with this silly one, but let me see if I can show you this one, this link that I posted on the Canvas side. Yeah, so if you go to the Canvas side, hopefully it works. If you go to the Canvas side, yeah, if I find like useful animations or things like that, I'll kind of like just be adding them here. I also posted if someone wants to learn more about like the clustering stuff, which again, we'll talk about it in more depth like later in the course. Like right now it's kind of like a motivation, but yeah, I posted kind of like this review, like which you don't have to read or anything, but sometimes it's just I'll just leave some stuff like that on the Canvas side so that if you want to find out more like reference or things like that, you can have like a reference, like a place that you can go to if you want to learn more about it. But yeah, like the one, I think the one that I wanted to show you was the second one. Let's see if that one works. This okay, let's see if this is the one that right, like the thing is like there are different types of clustering techniques. So the one that I'm doing, like the one that I'm showing you right now is called like the single linkage clustering, but there are other alternatives which I'll probably mention later on. But okay, let me do the single one and then I'll add some random points. Okay, let's see if this is okay, so let me explain what's going on here. So it generate again, you can think of this as data points and some measurements of some sort, right? So like what this is saying is that you start like with 24 random points, right? And um, so we're kind of like starting at step zero, where like the distance that I chose was zero. So if R is zero, no one is related with anyone else because you at least need some distance to go to the next point, right? So distance zero, that means that there's no relationship whatsoever. So everyone's kind of like an isolated island by its own, right? Nobody sees the other. And then if you just start clicking on next step, it kind of increases the value. It kind of finds the next distance where like there's some merging that happens. And it will use a different color for that. So let me see if I can show you how that works. Oh, let's see if I have to start clustering. Yeah, let's see. Started with okay. Yeah, so okay, right. So it gives a right. I forgot to press start clustering. So it assigns let's see how this is going to see. Let me I don't need to see this threshold here. Let me just okay. Yeah, I forgot how this works. Okay. Yeah, let me just see if I can reset it too, because I think now I know what it works. No, like let's add random points. Okay, so here's with 28 points. So I don't want to see this. Okay, so yeah, I think it starts with like step zero, starts with 28 individual points and separate clusters. I mean, it's trying to kind of give, I guess, 28 different colors here, although there are not that many colors. So, but it has there are 28 different numbers. Okay, so like on the right hand side, we can like see kind of like the 28 members on all by themselves. I think, yeah, like okay, okay, and then here what's happening. It's okay. Okay, yeah, but then why is this so far away? This dendrogram, like, is it maybe because it is? Okay, let me find like if this is like a nicer cluster to work with. Okay, so now I have 16 points. Okay, yeah, this one looks nicer because of this. They're not like as close to one another. Okay, so yes, now this one again explains actually. So you had these original 16 points, right? Each of them was their own island. at the beginning, and then it kind of like increases the distance until there's like the first merging that can happen. So in this case, and this is kind of like the diagram that you can see here, what this is saying is that of all these points pairwise, when you compare these distances, like the ones that were closest were 4 and 5. So if you kind of like increase the distance a little bit, that would be the first like two that can be combined into kind of like the same cluster. So that's why it assigned the same color here, 4 and 5. And it's being represented here kind of like by a link that you're creating between the two of them. Okay, if you increase and if you press on next step, okay, then what it's saying is that 4, 5, and 6, this triple could be the one that can be connected. Okay, so again, like you can see here like the relations, and then in fact, I don't know if you can kind of like see it too clearly because of the color, but there seems to be some edges that it tries to draw, kind of like say, oh no, there's like a bridge between them. And then you kind of like go on. Okay, so now these all get related. Now with the number 3 in addition. And then the next two are like what, 7 and 13. And 7 and 13 again are kind of like on their own. So they're their own cluster. And all the other points are still by themselves. But I mean, as you can kind of like see, you kind of keep doing this and you kind of like get this diagram on the right hand side. That's called like a dendrogram, if I'm pronouncing it correctly. But it kind of like shows all the like the relations of how the clustering is taking place. So for example, if you go at a particular height, you know, if you go at a particular height and you make like a cut, that kind of like tells you which ones have been merged at for that particular value. But the nice thing of having it here, like on the right hand side, is that it kind of like gives you kind of like how the connections are being made. If you think about it as kind of like a social network. So you can, like the analog of like and like a distance here is kind of like similar to saying, well, you connect, you two people are related if you can find like a chain of people that like they're all like in pairs, like friends with one another or something like that. That would be kind of like there's like in mathematics, there's like a common joke of like your Erdos number, if you have heard about it, who was like a famous mathematician. So it is kind of like, I think, okay, if you're Erdos, who said it already, by the way, but if you were Erdos, so your number is 0 because you're yourself. Then Erdos number 1 was like the person who, any person who published with him on the same paper. Erdos number 2 was a person who published with someone who published with Erdos and blah, 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 blah. And then there's like this, they did the same for like a Hollywood actor, like just like as a joke. And I don't remember who was the Hollywood actor that they chose, if someone remembers that, but it was one of like, you know, like not Tom Cruise, but one of those. Like what is your Tom Cruise number? Like like so it's like if you're Tom Cruise, it's Tom Cruise number 0. If you were in a movie with Tom Cruise number 1, and then Tom Cruise number 2 is that you're in a movie with someone who was in a movie with Tom Cruise and so on, which is similar to this like interconnectivity number, which probably you've heard of, like that every two humans are separated by 7 people. I mean, something like of that sort, which probably is like an average. I doubt like it's like literally true, but it's probably true for like large majority of like humans. Bacon. Oh, right, like the Kevin Bacon number. Yeah. So like, yeah, like that's the one that we chose. But it's kind of like this kind of like it's something similar, as in like we don't have like a preferred value for connecting them. So let's just analyze all the possible values. That again, like we'll create like a filtration, which is some terminology that I'll give you later on. But and then they kind of we kind of like see, you know, when does the merging happens, like which clusters kind of like persist on their own for longer periods of time. So you want to kind of to analyze all those behaviors for the entire value, like family of values that you could get, instead of like just choosing your favorite value in the world, because why did you choose that one instead of another? So that is what's nice about this, again, is that it's kind of like the dendrogram, it kind of like has all those relationships kind of like in a diagram where you can kind of like see it more clearly how the merging is going on. And again, I left this link on the on the canvas side if you want to play with it. But yeah, like it's just since it generates the points randomly, sometimes it's easier to kind of like see it if they're kind of like arranged in a particular way. Um, is that okay? Is that making sense? Okay, so now what I'm going to give you is some other examples of like equivalence relation, some in linear algebra and some in topology, so that you see that they are kind of like omnipresent in many different places. Okay. Um, let's see. Yay. Oh my God, let's see. But yeah, just to kind of like summarize what's the idea about an equivalence relation. The important feature that it has is that when it kind of like breaks up the space or the set into pieces where on each, that's called like a partition where kind of like elements of different like components are not related to one another. So in the, let me write that down. If you have an equivalence relation on a set, it decomposes. And by decomposes, it means like breaks up into subsets with the property that no two elements of different subsets are related to one another. I'll kind of do it with the example of the majors in a moment, are related to one another. So this is called like a partition. So for example, like yeah, in the example when we were talking about the relation about majors, like if my set S, like let's think of S as a set of students, if it had been like Alice, Bob, Charles, Diana, Kevin, let me just put like two more names, Emily, and then Peter. Okay. Right, so the set has like seven members. In this case, that's easier for me to draw the picture, right? And if you're relating them, if they have the same major, because that's an equivalence relation, you can think of kind of like in this diagram notation of like the Venn diagrams for a set, you know, that you're kind of like breaking up the set into kind of like regions or clusters. So if say Alice, Bob, and Diana are all biology majors, yeah, I'll put here like the letter B for biology. So they are related because the three of them are biology majors. They are all related to one another, right? But again, Charles and Kevin, they may be mathematicians, right? So they are in math. And maybe like I don't know, Emily's in philosophy, but like herself. So that's her in philosophy. And Peter, like, I don't know, it's like, computer science, CS. Okay. And also by himself. So Emily by herself, Peter by himself, and like, Alice, Bob, Diana in their biology group, and Charles and Kevin in their like math group. So they kind of like break up like, the set into four subsets, right? The biology subset, the philosophy subset, the computer science subset, and the math subset. And those subsets are called partitions. So you can, because it partitions, like for example, that's said into these joint pieces, the idea is that, there's no element that belongs to both of them, and they're completely unrelated, right? So Diana is not related with Emily because their majors are completely separate from one another. Okay. And there's like a kind of like a common term notation, which is called like the equivalence class of a set of an element. So let me just write it down in this example. So just to kind of like so that if you ever take discrete math or intro to math reasoning, you do a lot more of this stuff. But this is called the equivalence class of an element at X. And those are just like all the elements that are related to X. Consists of all the elements. So for example, in this case, let's just do it for each of them. What is the equivalence class of Alice, right? The equivalence class of Alice are all the students with the same major as Alice, right? So the equivalence class of Alice are all the students with the same major as Alice. So Alice has the same major as Alice. It's Bob and Diana as well, right? The equivalence class of Emily is just Emily. And the equivalence class of Peter. Oh, sorry, like this one should have been in kind of like set notation, so kind of like some brackets, not the equivalence class of Emily is just Emily. The equivalence class of Peter is Peter because again, Peter's by himself, and the equivalence class of Charles is Charles and Kevin. Okay, so making sense, writing it down. And notice like something that's subtle, like that, it kind of like implicit of how I'm writing it, right? Like the equivalence class of Charles is also the same as the equivalence class of Kevin, right? Because they both are in the same set. So for example, also notice also that you know the equivalence class of Charles is the same as the equivalence class of Kevin because you know they are in the same partition in the same cluster, and the same with the first one, right? Like the equivalence class of Alice is the same as the equivalence class of Bob, as a which is the same as the equivalence class of Diana. So there's no need to repeat it, right? Because if you just write the equivalence class of Alice, you simultaneously are referring to the equivalence class of Bob and the equivalence class of Diana. Okay. Okay, so making sense. And the thing that kind of like just to give you like a more mathy example, like like there's this thing like of like arithmetic like modulo a prime or like a number like where you could say for example the two integer, which is kind of like what's happened with the days of the week, right? Like if you say Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, it kind of like starts repeating itself. You don't have like a name for an eighth day. Same with the times of the day, right? Like, you could say 13 hours, but that's kind of like, you understand it also as 1 p.m., right? So you could say, like, well, let's just stick with the case of like 7, you know, like you could say that, so like this is called sometimes arithmetic mod 7, that two integers are related if their difference is a multiple of 7. So two integers. So, I mean, that is very easy to check this equivalence relation. So you can think, oh, what are the equivalence classes, right? So what is the equivalence class of 1, right? That consists of, you know, like it would be 1, it would also be 8, right? Because 8 minus 1 is 7, so there's a multiple of 7. It would also be like, 15, right? Because, like, 15 minus 87 or 15 minus 1 is 14, which is a multiple of 7. So essentially, you start adding 7. Once you start with 1, you just keep adding multiples of 7 in any direction, because you could also work with negative values. So, right, like you could have 22, or you could have -6, -13 would be the other one, etc., etc., right? Or like, for example, like the equivalence class of 0 is kind of like a nice one, right? It's 0, 7, 14, 21, 28, -7, -14, blah, 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 right? And you can do it for the other, like, there would be what? There would be also, there are actually 7 equivalence classes, right? Like there's one also for 2, another for 3, another for 5, another for 6. And after that, it kind of like starts repeating itself, because the equivalence class for 7 is just like 0, right? So there's another one for 2, another one for 3, another one for 4, another one for 5, and another one for 6. So, when you do arithmetic mod 7, there are like 7. And I mean, that's what you have, when you work in binary, you kind of like do the same, right? With binary numbers, it's just like if their difference is a multiple of 2, which is kind of like the most simple one that you could do, right? So that's why, like computers, like it's convenient to have that for computers, like both. But like you can do this for any integer. You can establish this like equivalence relation for any integer, and then you can kind of like, the nice thing is that you can kind of like work directly with equivalence classes. So, for example, you can add them, right? Like, so for example, you could define. Uh, of course, like if this were like a proper proof course, you would check that all of these things can be done. Um, you could add 2 equivalence classes just to be the equivalence class of their sum. And again, you have kind of checked that it kind of is fine. But so, for example, if from this perspective, you know, what would be 6 plus the equivalence class of 6 plus the equivalence class of 5? Well, that is the same as the equivalence class of 11, right? But where does the equivalence class of 11 land? 11 is 7 plus 4, right? And the 7 kind of like, it's kind of like the same as 0, so right? Like that's the same as the equivalence class of 4. So it's all that I'm saying is kind of like in arithmetic mod 4, sorry, mod 7, right? 6 plus 5 is 4. So with, of course, like that's not how regular numbers work, right? But it kind of like, if you think about it in terms of days of the week, right? That is actually how you would count days of the week, or days of the year, but that's arithmetic mod 365. Like if it's not like a leap year, right? Um, uh, and then, And you can also multiply them that way. So like you could also multiply two equivalence class with this arithmetic, you can multiply two equivalence classes the same way. If you want to multiply two equivalence classes, that's just like the equivalence class of the product. So again, like for example, what would be 6 times 5 in terms of equivalence classes? It's like the equivalence class of 30. But again, what is 30? 30 is 2 plus 28, right? And 28 is kind of like just like a multiple of 7. So 28 is kind of like 0 in arithmetic mod 7. So it's just like the equivalence class of 2. And these types of things are very used in number theory and a bunch of other different things. All that I'm saying is, the reason why I bring this up is because it kind of like, you can kind of like take very seriously like the equivalence classes and just work with them as like new objects, which is like what is a lot done in mathematics. And actually, I was going to show you some examples which are more relevant to what we want to use them for. But it's always like nice to start with a more concrete one, because in a sense you kind of have said this before, because when you compute times, that is literally what you're doing, right? Like if you're at 11 p.m. and you say, oh, let's meet in 2 hours, you're saying, oh, you were meeting then at 1 a.m. So you did arithmetic mod 12 in your head without even thinking about it. Okay, does that make sense? Okay, so let me give you now some more interesting examples. First, like in terms of like spaces, and then I'll do a linear algebra example, which will be really important for the next class. But I'll do some examples with spaces first. Like a very concrete one, which you again probably you have seen it, but not like from this perspective. Um, so here's like some equivalence classes on spaces. Classes. So like first one, like a very simple one. Imagine you have the intervals, let's say 0, 1. Well, 0 to pi, just to kind of like make the connection more clear, right? So you have like the interval 0 to 2 pi. So this is the interval on the number line. And the equivalence class will be the following. So I'll say that it's going to be a very simple equivalence class. So I'm just going to say that. So I'm going to say that if you have two numbers on the number line, x1 and x2, right? I'll say that these two numbers are related to one another. If one of the two things, if whenever like x1 and x2 are the same, in two cases, x1 and x2 are the same. Okay, so if they are the same number on the number line, on the interval, we'll say that they are related. Or the other case is when either of them is like one of the endpoints, or by the way, this is kind of like the math or, which is not exclusive, meaning that it's okay for both to happen simultaneously. So or they are like the endpoints. So like x1 is 0 and x2 is, for example, 2 pi. So So in other words, what I'm saying is that in this particular equivalence relation, 0 and 2 pi are related with one another. Okay. Oops. So it's kind of like a funny equivalence relation because if you're not 0 nor 2 pi, you're only related with itself with yourself. But if you're either 0 or 2 pi, you are related with one another. So the endpoints are related, and everyone else is just on its own. Okay. So so kind of like in a pictorial way, the way to think about it, imagine if like you were like an ant, like walking on the interval. So maybe you start at 0, you are walking, boom, 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 boom. And once you get to 2 pi, you, for all practical purposes, are in the same spot as 0 if you're working with equivalence classes, because 0 and 2 pi are the same equivalence class. So it is like an ant that lives in a space with the funny property that once you get to 2 pi, you get to where you return to where you started. There's a name for that. That is a circle, right? So like the equivalent class, if you work with the equivalence classes, again, like there's like a way to make this rigorous. It is literally a circle. So that's what is a circle? A circle is an interval where you glued, like you can see me do it. It is an interval when you put with glue the endpoints together and consider them like as the same point. Okay, so big pictorially, like the equivalence classes in this case can be thought of as a circle. So pictorially, this gives you the equivalence classes give you a circle. Classes in this case can be represented by a circle, and that actually is fun. In this case, can be represented by a circle. So it's kind of like taking the interval. Again, you kind of like take the interval and you put some glue at the endpoints and you kind of like stick these 2 points together. So this point represents simultaneously 0 and 2 pi. And in fact, that's kind of like a useful way to think about it in terms of like a periodic function. Because what is a periodic function in Calc 1? Like, maybe like a function for which x is like the same as x plus 2 pi, right? Like, for example, right? So if you have like a periodic function, that's why I chose like the interval to be 2 pi, because you're more used to like the period being 2 pi. Well, another way to think about a periodic function is that it's actually like a function on the circle, defined on the circle. And that's kind of like makes like a more clear connection like to Fourier series and other things if you've seen that before, because like from this perspective, that gives you like a function on the circle, because a periodic function is, if the 2 values agree at the endpoints, you can kind of like think that it what's actually defined on the circle. So it can be thought of as a function defined on the circle. That's like a very elegant way to think about a periodic function. Okay. That making sense so far so good. Okay, here's like a more cute example. Which if you ever play video game, like I'm sure you have run into this situation. So let me just start with the video game perspective. I have it here. Okay. So you're a rat and you're trying to find the cheese. Okay. So I have to control the rat. Let's see. But okay, so I can move my rat. Okay. But I'll do it in this kind of like video game perspective. I'm sure like, this is like a very common thing that if you get to this point, the rat starts appearing on the other side, right? Let me see if I can do it in a place that's a little bit more, right, like it happens in a bunch of video games, right? Here you are, right? Like you have seen this multiple times, right? Like this is very common. So, okay, so what's happening here? Okay, like the rat is not playing right? Like the maze is not in a piece of paper, literally, right? Because a piece of paper doesn't have this property that when you get to one of the edges, you reappear on the top edge, right? So like, in fact, like if you kind of like think about it of how like the game is being played, like of like the four edges, once you get to the top edge, right? So let me just cancel this out, right? Once you get to the top edge, you reappear at the bottom edge. So kind of like from our perspective, like the two edges, the top and the bottom, are indistinguishable from one another. So you can imagine creating an equivalence relation where you say every point on the top edge is related to the corresponding point on the bottom edge. So as an equivalence relation perspective, you kind of imagine gluing them together. So you glue those two together. Okay, and kind of like something similar happens with the other two edges, where like if you get to the left edge, you reappear on the right edge. So just like if this were like made out of more flexible material, just imagine like stretching this out like it's a tube, and you put some glue here and here, and you connect them, and you get a donut, right? So in fact, this rat is the game is being played on is a donut, or like whatever translation likes to call like a donut. So like all these games from the 80s or Pac-Man or whatever, like they're actually being played on a space that is a surface, which is not like a flat, it looks curved because it looks like a donut. So it has like an interesting shape. And in fact, there's something similar you can do, like kind of like a 3D version of this, which is like imagine kind of like the same story, like if you were playing like a 3D video game where like whenever I get to the floor, I reappear on the ceiling. Whenever I get to that wall, I reappear on this wall, and whenever I get to that wall, I reappear on that wall. Oh my God, yeah. Let me see if I can show you that. Oh my, wait, can you see it? No, like I think let me see if I don't think it kind of like shared the, let me see if I can open it again. I think it's not curve spaces. Let me see if I can do it again. Okay, yeah. So wait, can I? Oh yeah, yeah. So now I'm reaching to one of the walls and I reappear on the other side. And I get to one of the other walls and then reappear on the other side. Oh, you see, like it's kind of fun if you look at the Earth shape of the Earth because you can kind of like see the continents. So you see where it's kind of like the perspective that it's taken. But that, like if we're playing the game in a space like this, where like this gluing is taking place, it's actually again, it's not like the regular three-dimensional space because in three-dimensional space you don't reappear on the others. I mean, it's not that this is the other side because they have been glued together. It's just like it's kind of like a way of conceiving the space, and this is called like a three-dimensional torus. So in fact, like that has that has astronomical consequences because like, if you wanted to determine what like the shape of like the spatial shape of the universe, if the spatial shape of the universe were like a three torus like this, it could be seen on the distant sky galaxies that get repeated, like just because of the way light would travel in that universe, right? Because it could, you could have like, oh yeah, the example I always do. Let me see if I can draw it out. Um, it is actually like it's a subtle point, like if you wanted to determine what's the three-dimensional shape of the universe, because like just to do like kind of like the 2D version of that, like you could have here like planet Earth, right? And you have like a distant star here, right? But like if light travels in all directions, there's like a rate of light, like let me see if I can draw it. Would appear that way. But also there's this other rate of light that is traveling in that way. So you would see that same star in two different spots on the sky. You know what I mean? So you have to be, you know, if like the shape, the spatial shape of the universe were like that, you have to be careful not to overcount. I mean, there are other things, of course, like these light have traveled more. There's astronomical effects that happens with that, and Doppler effect. I mean, there's a bunch of like other considerations to have. But all that I'm saying is that, you know, that you could start getting into this type of things where like maybe you see galaxies that seem like copies of one another, but they could just be like the same galaxy. It's just that light travel like in different paths to the same place to Earth. So like that kind of like um create some interesting problems. But the point that I'm trying to say is that it is related to this equivalence relation stuff that we're talking about, because again, like a way to conceptualize it is that you had like the piece of paper and you created like an equivalence relation, you know, where you are identifying certain edges, and that the equivalence classes like gives you like the donut or things of that sort. So let me just like I'll draw the diagram that's very common in topology. So you have it around, and then I'll just finish for today with an example from linear algebra. So so the usual diagram is that you have like a piece of paper, and then like kind of like in the Pac-Man game, or like the thing that I was mentioning with the rat, these two edges are identified, they're glued together, and these two other edges are like identified, like I will use a different color. And that produces like the equivalence classes of that is like a donut. Equivalence class forms a donut. So in fact, like this is periodic in two directions. So it's kind of like a multi-dimensional Fourier. And you can do kind of like, if you had like a function defined or something like this, it has like two different directions, which are periodic. So you can do like a Fourier decomposition into periodic modes. Like, I mean, again, like it has many relations to other things. Equivalence relation is a donut. Again, like a donut is called like a torus by a mathematician. So I'll put the name here. But the thing is, like, again, like, of course, you can kind of draw it out this way, but kind of like this example in the 3D case with the room, I cannot draw how it would look like. So the only way to kind of understand it is just like kind of drawing like a diagram of how this works. That making sense of okay, let me finish today with an example from linear algebra, which would be super important next time. It's called the quotient of a vector space. I'll tell you what that is. I'll do it in a very concrete way, but it's a good thing to think about. So this is like this is one of the most important equivalence relations of the entire course. Like, in fact, it may be the most important equivalence relation for this course. So okay. So the technical name for it is called like the quotient vector space, but I'll tell you what that means. So the setup is that you're going to have a vector space and you're going to have a vector subspace inside of it. Okay, so you have two vector spaces, but one is kind of like a vector subspace of the other. And I'll kind of like do an example in a moment. So just to have something like in mind, so you have like a vector space V. And a vector subspace W. So again, like with vector spaces, you know, if you want to do like kind of like a diagram, it's kind of like a bit silly sometimes because but like an example of that could be the following. Like your vector space could be like, for example, R3. Your vector space could be R3, and the vector subspace could, for example, be the xy plane, okay? Just to have something very simple. Right, so R3 is just like the triples of pairs, right, where X, Y, and Z are real numbers. And then the subspace that I'm talking about is the XY plane. So you can think of the XY plane as just like the triples where like the Z is zero. Oh, well, yeah, you're right. Like it's just right. You're big. Thanks. Oops. Uh, right. So and then W could be the XY plane again, which again concretely you can think of it as like triples where you set the third coordinate equal to zero, right? So I don't know like how long ago you took linear algebra, but what was a vector space? Something where like you can add the elements together, that's still a vector. You can multiply the vector by a scalar, that's still a vector. And a vector subspace is essentially the same definition, it's just that it just happens to be within a larger vector space, right? Like that's kind of like the the idea. And if you wanted to draw like a picture, right? In this case, well, R3 would be the entire three-dimensional space, right? So I'll just draw like that on the XYZ axis to go and represent all of R3, you know. So all of space, all of 3D space. And then W kind of like sits, it's like the XY plane, which is like the usual one from Calc 3, right? Again, it requires a little bit of perspective, but I actually like it. But so when you have a vector space and a vector subspace, there's an equivalency relation that you can establish. And the equivalence relation is going to be the two vectors are related if their difference belongs to the subspace. Okay, so we'll check that that's kind of like, So here's like the equivalence relation that I'm going to, talk about. So here's like the equivalence relation. You say that two vectors v1 and v2 are related. v1 is related to v2 provided v1 minus v2 belongs to the subspace. Okay, so you have two vectors, you subtract them. If that belongs to the subspace, then they're related. If that doesn't belong to the subspace, they're not related. So we can kind of like check that let's just check quickly the sign equivalence relation because like the proof is very simple, but it's still, useful just to go over the definition of like an equivalence relation. So no, why is it reflexive, right? Okay. Reflexive just meant that every vector is related to itself, right? So why is V related to V? What that means is that you subtract them, right? And when you do V minus V, you get the zero vector, right? So you get since V minus V, right, is a zero vector. And like if you remember in a vector space, you always have the zero vector within it, right? Like the zero vector is always within any vector space. So that's in V, but it's also in W and it's also in any vector subspace. You know, almost by definition of like what a vector. In fact, if you remember like these true false questions of linear algebra, sometimes they'll give you a set. They ask you, is this like a vector subspace or not? I'm a way to check that it wasn't, it's because the zero vector wasn't contained, so that was a kind of useful one to check, right? Then why is it symmetric, right? So symmetric, sorry, just to go back. So symmetric, okay, what happens if V1 and V2 are related? That means that, in which order did I take it? That means that V1 minus V2 is in the vector subspace W, right? So what does that mean? That just means that their difference is on vector W, you know. So V1 minus V2 is on vector W. I don't know which vector it is, but it will be some vector W, which lives in this subspace W. I mean, I'm using the W in two different ways, right? Like uppercase and lowercase. But then why is V2, notice that V2 minus V1, right, is minus V1 minus V2, right? Like the usual trick of like factoring a negative sign, and that would be minus W, right? So this is minus W. And again, because you're a vector subspace, if you multiply it by a scalar, that's still in the subspace. So you see that you're kind of like going through all the properties of being a subspace, so this is still a vector in the subspace. And I'll show it to you like in a moment, with the example with R3 and the XY plane, so that it becomes a little bit more concrete. And then the transitivity is just uses a property that the sum of two vectors is within, is within the subspace, right? And so for transitivity, right, if if V1 is related to V2 and V2 is related to V3, what that means is that V1 minus V2 is a vector W, right? And V2 minus V3 is a vector W prime, right? Then what is V1 minus V3? The trick is to add and subtract V2. So V1 minus V3 is V1 minus V2 plus V2 minus V3, right? But V1 minus V2, that's just W, and V2 minus V3 is W prime. And that gives you something in the subspace, because again, like a vector subspace has the property that the sum of two elements is another element. Okay. That okay? Is that making sense? So that it's kind of like it's like if you had chance to see like equivalence relations in linear algebra, it's kind of like a simple enough proof that you can actually run it in that course if you already knew what an equivalence relation is. It's just that if you don't go over what that is, like you cannot really run this proof. But it really almost just uses the definition of what it means to be a vector subspace. That you can add vectors and then you can multiply them by a scalar. That's all, and the zero is always inside the sub. So just to kind of like wrap it up for today, I'll do how does this look in this example, and then like next time I'll do kind of like the general case and like and show you why this is a useful thing. But in our example, back to our example, of like R3 and the XY plane, right? What I like about this example is that it's very geometrically easy to understand what's going on here. Because if you had two vectors, V1 and V2, right? In fact, I'll use kind of like X1, Y1, Z1. I'll use kind of like the more traditional notation with the arrows, right? And V2 is like X2, Y2, and Z2, right? So here, like the condition for them to be related, right, is that V1 minus V2 is on the XY plane, right? So V1 and V2 are related if their difference is on the XY plane, right? If V1 minus V2 is on the XY plane, right? That's like because the subspace tells you is in this case the XY plane. But what does it mean for it to be on the XY plane? Well, if you do V1 minus V2, right? Like that's just like X1 minus X2, Y1 minus Y2, and Z1 minus Z2, right? Like that's what V1 minus V2 is, right? As a vector. So for it to be on the XY plane, the requirement to be on the XY plane is that the third coordinate must be 0, right? So that requires, so this needs, so Z1 has to be equal to Z2. In other words, in this case, the condition for two vectors to be related is that they kind of have the same height, with respect to the XY plane, right? Like they are at the same height above, or, if they have height, all the vectors at height 3 are related to one another, or all the vectors at height 5 are related to one another, etc. So as a term, in terms of like a picture, so like what that means like is that so the vectors must have the same height. And once you realize that, what is the equivalence class of a vector? So if I had a vector, right? Just to go back to this notation of equivalence classes, right? If you have a vector to be related to this vector, sorry, I should have called this x1, x1, xyz, sorry about that. Wrong notation. If you have a vector that has entries x, y, and z, right? What I'm just saying is that the vector that are related to this one will have the same z value. So there's a very obvious vector that's related to this one, which is 0, 0, z. So, and so all the equivalence classes are basically represented by the z-axis. So the z-axis represents all the possible equivalence classes in this case. So all the different equivalence classes make up the z-axis, right? Because if you start giving different values to z, that kind of just gives you the entire z-axis, which is a vector subspace perpendicular to the original one. So you can think of these as the orthogonal complement. So that's what I'll get to next time. But so let me just write this down like a good place to wrap up. So the different equivalence classes make up the z-axis, which is orthogonal, right? Orthogonal to the xy plane. And that would be more or less true in general. So next time, what I'll tell you is that, in the general case, like the equivalence classes can be put in correspondence with the orthogonal complement. Okay, next time, the equivalence classes. So if you have, I mean, again, like, I don't know how much you remember about the orthogonal complement, but I'll remind you like the basic properties about that. But the nice thing, and that's what that means is that it is a vector subspace itself in a sense. And then you can find its dimension and a bunch of different things. So like that's where we're headed. And we'll do some variations of this next time, which we'll start applying to graphs and like networks, simplices and other things. But this is like a good place to end because I think I already did what I wanted to do for today. So we'll continue talking about this on Thursday. If that sounds good.